Until now, what we've been doing with parametric equations is I would give you a pair of parametric equations and either would ask you to eliminate the parameter and write them as a single equation just in x and y. In other words, get rid of the t. Or I would give you a pair of parametric equations and ask you to draw a graph. In this video, I'm going to give you a graph and ask you to come up with a pair of parametric equations. Now, we know how to do that to a certain extent with regular rectangular equations. If I have a line, in this case a line segment, that goes between the 2 points 1, 3 and 5, 2, I can figure out what its slope is, the slope of that line. It's the second y minus the first y over the second x minus the first x. In this case, that's going to be negative 1 over 4, negative 1/4. And then I can plug that into an equation. Y minus, I think I'll use this point. Y minus y1 equals m times x minus x1. And then I can simplify. I don't really need to, but I could if I wanted. But that doesn't tell me a lot of things about the line. It tells me some things. It tells me what the rate of change is. It tells me what a couple of points on the line are. But this equation is missing some information. What if I said this was the point where my graphing started? In other words, this is where t equals 0. And then for the sake of argument, I'll say that this is where t equals 1. Now that could be t equals 2 or t equals 10. I could have other points in between here that were t equals 1, for example, and then this one could be t equals 2. But for convenience, I'm going to say that this is where t equals 1. If I make myself a table of values, much like the one that I made when I was learning how to graph parametric equations, it might look something like this, except in this case I'm just going to have 0 and 1 in my table, and then I'm going to have an x and a y. Well, the x, y pair at t equals 0 is 1, 3. So I have a 1 there and a 3 there. The x, y pair when t equals 1 is 5, 2. So I'll have a 5 there and a 2 there. Now, ultimately, what I want is an equation that says x equals, and it's going to have some stuff with a t in it. And then I'll have y equals, and I'll have some stuff with a t in it. What I've done in the past is I've started with these two equations, made a chart, and then graphed them. This time I'm working backwards, but what I want is a way to write x that only involves t. So I'm going to look at the relationship between the t values, the output for the t values, the two different t values just for x, and the output then just for y. In other words, I'm splitting this up into two different problems, one for x and one for y. So really what I want to do is figure out how does t affect x, and then how does t affect y? And since it's actually t's effect on x, one way to look at this is to say, what is my input? T. What is my output? X. And separately, what is my input? T. And what is my output? Y. So this is equivalent graphically to saying x equals, and in here there will be stuff with t's in it. And this graph is going to be the representation of y equals and stuff with t in it. So I'm going to focus on the x coordinate first. I want to see what the relationship is between the two different values for x, just for x, not for y, based on what t is. When t equals 0, t is usually time, not always, but when t equals 0, x is 1, and when t equals 1, x is 5. And I can graph that in its own way, separately from y, basically by treating the t as the input. This would normally be our x axis. T is my input variable, my independent variable, and x is my output or my dependent variable, just for this column here. Well, for this pair of columns. So I'm treating this like it's an x-y pair, where t is the input, right? X is normally the input. Anyway, so if t is 0, x is 1. So I'm going to have at t equals 0, I'm going to have a value x equals 1. At t equals 1, when t equals 1, x equals 5. So I'll have, I didn't really leave myself enough space here, did I? Let me make my axis a little bit longer. 1, 2, 3, 4, 5. When t equals 1, x is 5. So now I can see the relationship between t and x. And then I'll do the same thing for y. I'm looking at the relationship between the y output values for the same two input values for t. So here, when t is 0, y is 3. So I have a point there. And when t is 1, y is 2. So I have a point there. And so now I can see graphically what the relationship between y and t is. Now, in just the same way as I found the equation of this line by doing some algebra, I can find the equations of these two lines by doing some algebra. So let me do that. I have a slope here for x. I have a slope of 1, 2, 3, 4 over 1. So my slope is 4. And normally, I'm going to write my equation up here, my formula. Normally, I'd have y minus y1 equals m times x minus x1. And I'm going to use the same formula, but I have to keep in mind that the role of x is now being played by t, and the role of y in this case is being played by x. So this formula for this line is going to read like this: x minus x1 equals m times t minus t1. Now I know m is 4, t minus x comma t, or sorry, t comma x actually, is 0 comma 1 or 1 comma 5. You pick. I think I'm going to go for 0 comma 1. Zeros and ones are so much easier to work with. Now, if I distribute, I get, on the right-hand side here, just 4t, because 4 times 0 is 0. So I'm going to get 4t here, and then I'm going to add 1 to both sides. So that's going to give me the equation x equals 4t plus 1. And that is the equation for x in terms of t. Now I'll do the same thing for y. Again, my formula is normally y minus y1 and x minus x1, but again, x is being, the role of x is being played by t. In this case, y does equal y, but x equals t. So my formula this time is going to be y minus y1 equals m times t minus t1. Now this is the point 0, 3, t comma y, 0, 3, and this is the point 1, 2. I'm picking the t is 1 and the y is 2. So the slope here is 3 minus 2 over 0 minus 1, which is negative 1, sorry, it's 1 over negative 1, so negative 1. So my slope is negative 1. And I need a t comma y pair. So I can either pick 0, 3 or 1, 2. You can pick either one. I really like working with zeros. They make lots of things go away and they make algebra a lot simpler. But there's absolutely no reason why you couldn't use 1, 2 instead of 0, 3. I'm going to use 0, 3. That gives me y minus 3 equals, when I distribute here, I get negative 1t plus 0. And then I'm just going to add 3 to both sides. So that gives me y equals negative t plus 3. And that is the equation of y in terms of t. So now I have a pair of parametric equations. X equals 4t plus 1 and y equals negative t plus 3. And there you have it. The nice thing about this system is that it's not the only right answer. If I had a different point in here, if I could figure out what that point was, or I was given multiple points, then I could choose a different point other than 1, 3, 5, 2 to use as my t equals 0. I could have used this point as t equals 0 and this one as t equals 1, reversing the process. There are different ways to get the right answer, but this is an easy one. And one of the reasons I wanted you to see this is because this process of breaking the graph up into just what is x doing in terms of t and what is y doing in terms of t is going to play a large role in what we do next. So one of the things I want to look at here before we move on is, what is y doing? What is x doing? And what is y doing in terms of t? Now, remember that we said we were going to let this equal t equals 1. So between t equals 0 and t equals 1, I'm starting with the y graph on purpose because it's actually easier to see. And then we'll talk about the same thing with the x graph. Between t equals 0 and t equals 1, y goes from a height of 3 to a height of 2. And you can see that in the graph. Y goes from a height of 3 to a height of 2. The graph comes down from 3 to 2 over the course of the graph, the piece of the line that we're working with. So the change in y over the course of the graph, over the course of 1 second, if you will, is down 1. And that's pretty much it. That's all y is doing across 1 second. Now, x is a little harder to see because we're graphing it vertically here, but we have to look at it horizontally here. Over the course of 1 second, x moves from 1 to 5. So it looks like it should be really steep here. But if you go to the graph over here, what we're saying is that x moves from 1 to 5. So while I'm looking at a vertical change on this graph, I'm looking at a horizontal change on this graph. That's why it's kind of tricky. But if you just think about the values here, what is x doing? It's going from 1 to 5. What is x doing across t, across the entire graph? It's going from 1 up to 5. Down here at 1, up to 5. From down here at 1, up to 5. Here's another way that I like to try to describe this sometimes. Imagine that you're standing here and you're looking in this direction. In fact, what I like to do is imagine that I'm in a glass elevator and I'm looking across, I'm looking sideways here. I can't see this graph from the front. I can't tell how much distance there is between 1 and 5 in this case, right? I can just tell that there is something. When I look out into space ahead of me, I can see that there's something there. If I drop the elevator a little bit and I look through here, then I'll see, yep, sure enough, there's something there. I can't tell how far away it is, I just know that there's something there. Let's say I get down to just above 2. Yep, there's something there. I can see something when I look through the side of the elevator. If I drop below 2, all I can see is that there's nothing there. Okay? Same thing as if I get above 3, there's nothing there. So what I can see is that there's something, when I look through the side of the elevator, there's something there between 3 and 2, or between 2 and 3. So it's as though I'm projecting, let me get my pointer again. If I project a light here and I project it onto this wall over here, I'm going to get a shadow between 3 and 2, but nowhere else. That's what y is doing. It's traveling between 2 and 3, and it's taking the course of t equals 0 to t equals 1, taking the course of 1 second or 1 minute or whatever our units are. Right? It's taking that long to do it, but it's only going between 2 and 3. And that's what this is telling me. Across 1 second, y is going between 2 and 3. Now for x, imagine that you're on a platform of some kind and you're looking down. If you look down here, you'll see, yep, there's something underneath me there. If you're standing here and you look down, yep, there's something underneath me there. Looking down here, yep, there's something underneath me. But if you look here, it's just the great abyss. There's nothing below you here, and there's nothing below you here. I can't tell how far up and down this line is moving from this perspective up here. All I can tell is that there is something underneath me between 1 and 5. That's what this graph is telling you. All I know is that over the course of 1 second or 1 minute, there's something between 1 and 5. It starts at 1 and goes to 5. Y starts at 3 and goes to 2. X starts at 1 and goes to 5. But that's all I can tell. So again, the graph of y with respect to t is usually a little easier to picture. It's usually a little easier to figure out because it's moving vertically here and vertically here. whereas x is moving horizontally up here. We're looking at the graph in a horizontal way here, but we're graphing it vertically here. So that's the trick. Let's take a look at a slightly more complex graph and see if we can come up with the parametric equations for it. I'm making my notes kind of as I go along here, so I'm actually going to start down here in the bottom left-hand corner of the screen. In a previous video, I think it was just the last one, we discovered that the equation of a circle can be written as x equals r. We had a radius of 5, so it was x equals 5 times the sine of t minus the x coordinate of the center. So in that case, it was 3, because the minus 3, negative 3, because the center of the circle was at negative 3, negative 4. So x equals 5 sine of t minus 3, and y equals 5 cosine of t, and it was minus 4. H comma k is the center of the circle. In this case, the center of the circle is 0, 0. So I'm going to have no h and no k. The radius of this circle is clearly 4. So I'm going to have 4's here and here. Now, as it happens, I can write this either as x equals 4 sine t, y equals 4 cosine t, or as x equals 4 cosine t, y equals 4 sine t. The reasons for that will hopefully I'll remember to tell you at the end of this video. Now, the only reason I'm telling you the answer before we start is because I like to do that with early examples so that we can confirm that what we discover here actually is true. We know from a previous video that this is an answer. It's not the only answer, but it's an answer to the parametric equations for this circle. Now what I'm going to do, though, is I'm going to use the technique that we learned on the previous screen and apply it to finding out parametric equations for this circle that way. So I'm going to erase one of these because I don't want both of them to be on the screen. They'll be in my way. I think I'll try to put these, yeah, they'll fit there. That'll work. Now, I'm going to imagine myself standing on a platform up here and looking down. When I do that, I might be able to walk back and forth across this platform, and I'll see below me that there's nothing to the right of 4, and there's nothing to the left of negative 4. Everything's happening between 4 and negative 4. Now, more importantly, now that we're in a more complex situation, you might want to imagine this. Pick a point on the graph. Let's just put one right there. And imagine that point is traveling around this circle. Now, if you're standing up here, you can't see that it's going in a circle. All you can see is that it's going to 4, and then to negative 4, and then to 4, and then to negative 4, assuming you're going around the circle more than once. 4, negative 4, 4, negative 4. What are the coordinates of this point? This is x in terms of t. I put that point there. I'm not sure why I put that point there. I probably should have put it here. Let me try to change that. Now, having done that, there's nothing wrong with starting here, but because I'm trying to explain this to you, I wanted to start in a place that's easy to identify. Notice that it's at an extreme value for x. You could start here, you could start in the middle. I'm starting at an extreme value for x so that I can pick a point here, represent it up here. So what I'm going to do is I'm going to start by saying this is my t equals 0. The coordinates of that point are 4, 0. So when I graph x in terms of time, what I'll be saying is that at time 0, x is 4. For this graph, t equals 0 and x equals 4. So I have a point there. This point here on the x graph corresponds to this point on my circle graph, but only for x. All right, let's take a look now at what x is doing as time goes on. As I mentioned before, if you were standing up here, you'd be able to say, oh, look, it's at 4. Oh, look, it's going down to negative 4. Oh, look, it's coming back up to 4, and it's going back down. Why am I saying that? Because looking at it from above, I can't see it moving up and down. I can only see it moving back and forth. So it looks like it's going down to 4, negative 4, and then back up to 4. And then down to negative 4, and back up to 4. And what does that look like on a graph like this? Well, if it starts at 4, and goes down to 4, and then back up to 4, and then down to 4, and then back up to 4, and so on. It looks like a cosine graph. In fact, specifically, it looks like the graph of 4 times the cosine of my input variable t. Now, I've graphed 2 cycles here. Normally, I would only graph 1. We'll come back to that, and I'll explain why in a few minutes. But before we do that, I need to do the same thing now for y. So now I have to be in my glass elevator off to the side here and looking this way. When I do that, starting at the same place, all I'll be able to see is that my point starts at 0, gets up to 4, or it gets as high as 4, and it comes back down to -4, and then it comes back to 0 again before it starts a new cycle. So in terms of y, that point is starting at 0. Eventually, it gets as high as 4, and then it comes back down to -4, and then it goes back up to 4, -4, and back up to 0. If I make 2 full cycles of this graph, for y, I go from 0 up to 4, through 0 down to -4, up to 0, back up to +4, down to -4. But let's just do one cycle. Let's see if we can figure, because after the first cycle, the thing just repeats itself, right? So let's just see if we can figure out what one cycle is for both x and y, and then we can compare them. So starting at, I'll do y first. Starting at 0, I get up to 4, I'm back down through 0, on my way back down to -4. That doesn't have a negative on it. And then from there back to 0. That's one cycle. 0, 4, 0, -4, 0. And that's what needs to happen here. 0, 4, 0, -4, 0. And the rest of this graph is a little bit redundant. Now that looks an awful lot like a sine graph. Because its amplitude is 4, it's 4 times the sine of the input variable t. Okay, let's go back and do the x graph. X graph is a little trickier anyway. So now I'm standing at the top, looking here, starting here. My x value is 4, way up here at 4. It comes down to x equals 0, right? It comes down to x equals 0. It comes down to x equals -4, up to x equals 0, and up to x equals +4. So for x, I'm going 4, 0, -4, 0, 4. 4, 0, -4, 0, 4. And the rest of that graph is redundant. So now I have one cycle of this graph, sorry, my pen just stopped working there, this graph, for x and y independently, but they're still happening at the same time. My graphs are actually a little off here. Ideally, what I would want is for my t equals 0 to be there, and my t equals 1, which is the end of my time, to be there. And so my cosine graph's a little bit off. All right, I've spread it out there a little bit so that it better matches time-wise, t being time, what's going on with the sine graph. So if this is my t equals 0 for both graphs. This is my t equals 1 for both graphs. This is the beginning of one cycle. This is the end of one cycle. The point itself is traveling on a curve, and it's going to get back to where it started for both x and y at the same time, because the point is a point. It has an x coordinate and a y coordinate. It can't, as a point on the xy plane, it doesn't split off into 2 points, right? It's going to get back to where it started as an xy point. So it has to get back to where it started. The x and the y coordinates both have to get back to their original starting places at the same time. So now what I've just demonstrated is that the equation for x of t is 4 cosine theta, and the equation for y of t is 4 sine theta. X equals 4 cosine theta, y equals 4 sine theta. Here's the pair of equations I started with. But remember, I said at the beginning that you could write them either as sine and cosine or cosine and sine. So what causes them to be cosine and sine? What causes them to be sine and cosine? I know what causes them to be cosine and sine because I have that here. Well, the answer there is I started at x equals 4 and y equals 0. If I start at x equals 0 and y equals 4, let's try this in a different color. If I started here, then my x graph starts at 0. This graph right here, the x value at my starting point is 0. And then which direction should I go in? Should I go positive x or should I go negative x? I tend to go counterclockwise just because that's what we do in trig, but there's no law that says you can't go clockwise. So let's go counterclockwise this time and see what happens. If x is 0 here, right, remember that I'm standing up here looking down and all I can see is this particle moving basically back and forth. I start at 0 and then x gets smaller until it gets to negative 4. So that's going to be x starting at 0 and getting smaller until it gets to x equals negative 4. I'll try that again. Then it gets bigger until it gets to 0 again, and then it goes all the way back up to 4, back to 0, and then up to 4. And then finally, it comes back down to 0. Now I'm moving my pen up the screen, but I'm saying x is coming down to 0. Well, that's because I'm thinking in this direction. So x comes down to 0. Meanwhile, for that same point, if I'm now standing off to the side looking this way, just watching it go up and down, it's starting at 4. And it comes down to 0, and it keeps going down to negative 4, and it comes back up to 0 and up to 4. So in the terms of y, I'm going 4, 0, negative 4, 0, 4. And so I have 4, 0, negative 4, 0, 4. In the same amount of time as this graph. Now, my x graph this time is 4 times, well, close, 4 times the sine of t, but it's an upside down sine graph, so it's negative 4 times the sine of t. And my cosine graph is y equals 4 times the cosine of t. So this green pair is closer to my original answer here, a sine for the x and a cosine for the y. So how did this one end up being negative, and how come this one's positive? Well, I went in this direction. If I'd gone in this direction, I would have ended up with a positive. So there are multiple right answers. This is something else that's very important to keep in mind. We're going to be doing this a fair amount in the next week or so. This is just a taste. I wanted you to see this before the end of this. I want to call it a subunit because I'm going to draw a line here. You're going to take a quiz and an exam over this material, and then the last exam is going to be a project, and you're going to be doing a lot of this kind of thing for that project. So this is the end of this topic. This is the end of this section, this unit, and with the one exception of the project, it's pretty much the end of the course. I will do a few more videos because we're going to need some practice and we're going to need some guidance in figuring out how to come up with parametric equations for other graphs besides lines and circles. But for the most part, this is pretty much it for trigonometry.